Can you all see a PowerPoint type thing right now?
Yes.
Yep, and we can see you presenting now too.
Okay, cool. Yeah, so my presentation today is Modern Physics, Knowing the Limits of Knowledge. So the objective for today's presentations will be a basic qualitative introduction to modern physics. Most parts will be counterintuitive, so if you don't know what is going on, that is to be expected. There will not be any math in this presentation today, however. And the purpose of the presentation is to dispel with the fiction that the universe is like a clock, or that there's a clockwork universe of everything proceeding in an orderly fashion, one after another. So first we have a quote from Richard Feynman. And he was a Nobel laureate in physics. He got his Nobel Prize from physics related to quantum mechanics, and he said, I think I can safely say that nobody understands quantum mechanics. So if a Nobel laureate in quantum mechanics says no one understands it, if you all don't understand it after today's presentation, that is to be expected. And if you think you understand quantum mechanics after today's presentation, I can assure you that you are incorrect. Next, we have some words of wisdom from old Donald Rumsfeld, former Secretary of Defense. He said, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know, but there are also unknown unknowns. The ones we don't know, we don't know. And today we're going to be focusing on known unknowns. Those are things that we don't know, but we know that we don't know them. So the world according to Isaac Newton, this was kind of the state that physics was from when Isaac Newton lived hundreds of years ago, really until the end of the 19th, beginning of the 20th century. And Newton's philosophy can really be distilled down into three fundamental ideas. Those being, there's absolute time and space. That is that everybody can agree on 1 second is 1 second, or 1 foot is 1 foot, and that you can ultimately measure things using these agreed upon principles. Also, that things were intrinsically measurable. That is, everything can in one way or another be measured. There's nothing that's immeasurable, and everything, you know, as technology develops, as you get better and better instruments, your ability to measure things becomes better and better, and there's, you know, eventually you could potentially get to an absolute measurement, a true measurement.
I have a question on that one, on the intrinsically measurable.
Yeah, absolutely.
Do you have any opinion on if everything should be measured?
I don't know that specifically. I don't know exactly what his opinion on that was. This was a pre-vaccination world, but I can't say that specifically. And then he also believed that everything was deterministic and predictable. That is, if you were able to take all of these measurements, plug them into some set of equations or mathematics that described the fundamental behavior of things, you could ultimately predict the future. If you were able to get a bunch of data together, plug it into the correct mathematical models, you could, you know, for example, say the relationship between the moon and the Earth a year from now, 10 years from now, 100 years from now, really you could extend it as far out as you had the ability to process the information. However, the 20th century exposed Isaac Newton as a hack fraud. That is because his ideas of absolute space and time, things being intrinsically measurable, and things being deterministic and predictable are all incorrect. These were things that the 20th century showed us. The absolute space and time is undercut by the theory of relativity. Things being intrinsically measurable, undercut by quantum mechanics, and things being deterministic and predictable, undercut by chaos theory. So this presentation today is going to focus on those three things, being relativity, quantum mechanics, and chaos theory. So these modern physics of relativity, quantum mechanics, and chaos theory, when they apply, when they break down from what we observe in our day-to-day life, because the reason that Isaac Newton got the relationships and the mathematical equations he got was because in our day-to-day life, they pretty much match how we encounter things. It's when you really start to get to extremes of the universe that his equations and his analysis really breaks down. So relativity applies when things are either really large or really fast. So you think a star is something that's massive, and a spaceship that's going some large fraction of the speed of light would be something that's really fast. Quantum mechanics applies to things that are really small, like an atom. We'll see later in this presentation that this model of the atom right here is actually fundamentally incorrect. And chaos theory is when a lot of things are interacting. So you can think like weather, for example. You have huge systems throughout the Earth, a lot of particles, a lot of water, a lot of space, and that's what breeds chaos. So relativity, the history of relativity, just get an understanding of where it came from. It's proposed by Albert Einstein in 1905. He really brought about all of this information by himself. He didn't necessarily build relativity on other physics that existed. He more superseded things that already existed. And a lot of this just came from his ability to kind of simulate and process things in his own mind. And he sought to resolve problems from Newtonian physics regarding things that are really big or really fast. Basically, there were measurements about the speed of light that didn't really make sense based on Newtonian physics. And then there were also some specific things regarding gravitation between stars that Newtonian physics also wasn't doing a very good job of approximating. So what relativity fundamentally means is that the speed of light is the same for everyone. It doesn't matter how fast you're actually going, the speed of light always appears to be the same. So the speed of light for everybody in a vacuum is approximately 186,000 miles per second. So unfortunately, Leo wasn't able to join us today. However, I have a little example to work through in order to help us understand what it means for the speed of light to be the same for everybody. Here we have two people in space. We have Leo, who is just floating in space, going 0 miles per second, and Robert, who's created some sort of super fast spaceship that's going 180,000 miles per second. So Robert is almost going the speed of light. And they both hold flashlights as well. So my question is, based on our intuitive understanding of the universe and how things work, if both Leo and Robert turn their flashlights on, how fast will the light from their flashlights be going?
The speed of light.
Okay. So it'll be going the speed of light. So both light will be 186,000 miles per second? So that is correct, but that's not really intuitive. If we think about, let's say you're driving in a car and you have a baseball in your hand. You're going down the freeway at 60 miles per hour and you throw the baseball just like a little toss. It's only going a few miles an hour. To someone outside the car, it will look like the baseball is going those few miles per hour plus the speed of the car. So it might look like the baseball is going 65 miles an hour, even though you only give it a little toss, because that person sees the car going 60 miles per hour plus the speed of the baseball. For light, that is not the case. For light, all light appears to be 186,000 miles per second to everyone. So both Leo and Robert turning the flashlight on at the same time. From Robert's perspective, the light is going 186,000 miles per hour faster than he is. For Leo, his light is going 186,000 miles per second faster than he is. And Leo, looking at Robert's light appears to be going 186,000 miles per second faster than him, and likewise for Robert. So for everybody, the light appears to be going the same speed, even though there are these huge differences in how fast everybody is actually going. So the question is, how is this possible? And the reason that this is possible is due to the effects of time dilation, as predicted by the theory of relativity. Basically, if both Leo and Robert have a clock in their either spaceship or on their spacesuit that both of them can see both of the clocks, Leo, when he's looking down at his clock will appear to be running normal speed. However, when he looks at Robert's clock appears to be going significantly slower than normal speed. Likewise, when Robert looks at when Robert looks at his own clock, it appears to be running normal speed, but Leo's clock also appears to be running significantly slower than Robert's clock. For both of these individuals, the clock outside of where they are appears to be going much slower than their clock. And And one way
Can I chime in and ask a question / comment here that I think you're probably already getting towards?
Yes. Why is it that both people appear, because like intrinsically, again, you would think that Robert sees Leo's clock running slow, but Leo sees Robert's clock running fast?
Well, exactly. I would expect one person's experience to be different than the other person's experience. And I get that, like, with reference frames or whatever, to me, it could look like Leo's accelerating away at 180,000 miles an hour. I guess my other question would be then, to a neutral observer observing both of us, what would it be like? But the neutral observer, I guess, would just be Leo. Like Leo in this frame of reference, Leo is.
One thing about the theory of relativity gets to is that there's no such thing as a neutral observer. Neutral observers do not exist. And so one key to this actually is that there is no acceleration happening. That's fundamentally the reason why this is happening. So as Robert touched on, there's something called the frame of reference, which is basically, so Leo looking at Robert looks like he's going really, really fast. But if Robert looks back at Leo, Robert doesn't think that he himself is going fast. It looks like Leo is going really fast away from him. So for both of them, their frame of reference is what it's called is equally valid. So for both of them, it looks like the other is the one who's traveling really fast, and they are sitting still. It's like if you think about if you're ever on a train or on a bus, and the train or the bus next to you moves, or you're moving, it can get confusing as to which of you is actually moving. That's one way to think about frames of reference. So what relativity predicts is that those frame of references are valid. So when the actual changes in time dilation occur is during the acceleration moment itself. It's a little bit beyond the scope of this presentation, but ultimately, when Robert would accelerate, go really fast, and ultimately decelerate, his time on average is going slower than Leo's time. So if Robert went, I think I touch upon this in another slide, but if Robert went 180,000 miles per hour for 10 years, let's say he did a round trip journey and his average speed over that period was that 180,000 miles per hour. 10 years would pass for Robert, 40 years would pass on Earth. And the time when that difference in time or when the divergence in time occurs is during the acceleration and the deceleration. Because the acceleration and the deceleration are fundamentally different reference frames. You can't compare them if there's acceleration happening on one and deceleration happening on another, if that makes sense, Robert. When Einstein, it's a little bit beyond this, but when Einstein did it, he effectively said it's the act of acceleration and deceleration is what is causing the divergence in the actual times that both experience. What's that?
It doesn't actually matter how far he actually travels, nor the time that he is at that speed, just how long it takes him to accelerate and decelerate?
No, so that is why it's a little bit beyond the scope.
I was going to ask the same thing.
So there's been greater or more experimental looking into this, and it's not actually the acceleration or the deceleration. That is like a helpful approximation, but even if it was like a spontaneous change in speed, you would still get the time dilation effect.
Is it like the amount of energy that you're putting into something by speeding it up?
Yeah, so that is, it has to do with the fact that what relativity also predicts is that gravity itself can distort space-time. And the effect of the acceleration of the deceleration is doing a localized gravitational phenomenon that is distorting space and time in that location.
Right. I don't obviously get that entirely, but thank you for indulging the tangent. I think that's enough, though.
Yep. So a thing to be clear about this is it's not just that the clocks are moving at different speeds. It's that time itself has been warped and is fundamentally moving at different speeds for both. In addition, both see the other person as contracting in the direction of that they're traveling. So Leo looking at Robert, Leo would see that Robert's width is the same, but his length would contract, whereas Robert would see a contraction for Leo as well. So
I was going to say that that's a good weight loss plan right there, but I guess your weight,
no,
your mass goes up, right?
You gain mass as you accelerate. That's fundamentally, that going a little bit deeper again, that is why acceleration, because you can never hit the speed of light. You can accelerate, you can accelerate infinitely long. You can accelerate for 10 trillion years as fast as you want, and you will never hit the speed of light. And that's because as you get faster and faster, you get more and more massive, so more and more energy is required in order to incrementally speed up a little bit more. And in order for something with mass to go the speed of light, it would take infinite energy, because something with mass going the speed of light would have infinite mass. So why does this matter? So what? So what relativity basically says is that absolute space and time does not exist. Fundamentally, does not exist. We can say like, hey, 1 second on the Earth in like all these conditions means one thing. 1 foot on Earth means a bunch of different things, but 1 foot and 1 second throughout the universe, based on experience, it is not possible to agree on what 1 foot or 1 second is. Space and time itself can expand and it can contract. Things happening simultaneously depends on your frame of reference. So 2 events can happen at the same time for one person and different times for another person. And that has to do, again, with just the nature of how this all affects time. Energy and mass are interchangeable. So if you know the famous equation E equals mc squared, that arises from relativity. And it basically says you can freely convert mass into energy and energy into mass. It also means time travel to the future is possible. So if Robert took that trip, he averaged 180,000 miles per hour. A trip that took 10 years for him would take 40 years on Earth. So if you are willing to go fast enough, you can go as far into the future as you want. What this also means is that interstellar colonization and things like that are potentially possible, because if we sent a bunch of colonies out and they have spaceships that can go really, really fast, maybe in our lifetimes or our descendants' lifetimes, it might be, in 1,000 generations, they might not be able to actually have these colonies established. But from the perspective of someone on the ship, if they're going fast enough, they could travel pretty much anywhere in the universe within their lifetime. So some practical applications from relativity. GPS satellites actually perform time correction calculations. And that's because that's 2 effects. One, GPS satellites are going faster than us here on the Earth. So that's one effect. That makes it so that GPS satellites are going a little bit slower, or time is passing a little bit slower for the satellites than for us. However, conversely, GPS satellites experience less gravitation than we do, because we're on the surface of the Earth. GPS satellite is in orbit. So that actually causes our time to pass slower than GPS satellites' time. So combining those 2 together, gravitation is actually the larger of those 2 effects. So time on a GPS satellite is actually only slightly faster than time here on Earth. So GPS satellites, what they actually do is they calibrate their microprocessors to run at a slightly different cycle speed, so that it is set to like a standard cycle speed on Earth, basically. And then they periodically do just calculations in order to make sure that they're all matching time. Also, nuclear energy is possible because of relativity. Here you see the USS Enterprise, the second time the USS Enterprise has showed up in this presentation, the first time being the Star Trek ship. You see that the sailors on board are spelling out E equals mc squared. I believe that's the USS Bainbridge, maybe. That's another couple nuclear ships who are following alongside. Pat, it looks like you may have had a question.
Yeah, I started to think about, I was thinking, okay, GPS satellites are geosynchronous orbit, right? But then I thought about, okay, they are actually traveling faster than the Earth because they're so much higher up. So then I kind of answered my own.
It's like a record player. The further out you go, the farther or the faster it travels.
Yeah, okay.
Even though it's a rigid object.
Thanks for confirming.
Yep. Yeah, so next we have quantum mechanics. Quantum mechanics was much more incremental than relativity. It's, people building on top of each other a lot more. But the father of quantum mechanics is considered to be Max Planck, or Max Planck. Here we have a picture of old Max, a really dour-looking individual. There were additional important discoveries by Albert Einstein in 1905. He kind of had his hands in all the physics of these days. And actually, Albert Einstein was the recipient of a Nobel Prize, and he received his Nobel Prize for his work on quantum mechanics and never received a Nobel Prize for anything related to relativity. And the most commonly taught interpretation of quantum mechanics, that is the Copenhagen interpretation, was created by Niels Bohr in the 1920s. And this photo right here is Niels Bohr. He founded a physics research institute at the University of Copenhagen, and they did a lot with quantum mechanics. So quantum mechanics, what it means. Here we have a lot of people, when they think of an atom, this is what they think of. They think of a nucleus, and then they think of some stuff, some electrons orbiting around it. This, however, is not correct. This model is very simplified, and it kind of makes the atom, look like a planet with moons or asteroids or whatever else orbiting it. However, this does not actually follow the real behavior of atoms. The real behavior of atoms, this much better represents what is actually happening with an atom. When you see the black dot there, that is the nucleus. This is not to scale. The black dot there need to be much, 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 much smaller in order for this to be to scale. But the black dot is a nucleus, and that yellow-orangish area are the electrons. And that's because electrons don't exist as discrete particles. They're not, balls orbiting an atom. An electron is best described as a field of probabilities. So particle.
Can I chime in with a question?
Yes.
What actually is the Copenhagen model?
So that's basically the things I'm talking about here are the tenets of the Copenhagen model.
Are you going to talk about other models?
Is
it something I should Google myself?
That's probably something to Google yourself. The Copenhagen model is the most taught model of quantum mechanics. So particles basically exist as probability distributions. So if you look at this picture, you see some areas are lighter, some areas are darker. The areas that are darker are the areas that an electron is more likely to be in. The areas that are lighter are the areas that the electron is less likely to be in. And it is only when the electron is interacted on by an outside force that the electron actually chooses a state and is in a location. However, prior to it being interacted on, there is no way to say with any certainty where exactly the electron is going to be. There are only places where it's more likely the electron is going to be on one hand, or less likely it's going to be on the other hand. There's nothing you can say about the properties of the electron itself or the atom that would lead you to say it's exactly in this location. In addition, it is impossible to exactly know all properties of something like an electron. So for an electron, you might be concerned with its position and its velocity or its speed. You want to know, hey, where's the electron, how fast it's going? However, quantum mechanics says the more you know about its position, the less you know about its speed. The more you know about its speed, the less you know about its position. If you know its position as well as you can, almost absolutely, you know nothing about its speed. If you know its speed absolutely, or as well as you can know, you know nothing about its position. Yes, Robert?
How is that derived or figured out?
So that's from the Heisenberg uncertainty principle. That is basically, there is a Planck is like the smallest measurable point in space, and it's derived from that.
Was there an experiment or a thought experiment that got people to?
I can look into that.
Google. Okay.
That'd probably be another good thing to Google. A lot of it is just derived from mathematics.
Yeah, they never told us in physics. They just gave us the equation. So.
And what's also interesting is that for absolute, if you think about absolute zero, when something's at absolute zero, absolute zero is a coldest something can go. You can't cool something more than absolute zero. And when you would think about it, you would think intuitively, hey, if you can't cool something anymore, heat is fundamentally stuff moving around is what causes things to have temperature. So you think if something's at absolute zero, it has no motion. That's not true, though, because per the uncertainty principle, you can't say position absolutely. So if you were to say that something wasn't moving, and if something wasn't moving, because there's an absolute zero, you would say that its velocity and its position absolutely, which is not possible. So it's called this is just something to look up, it's called the zero state energy, is that base energy from the movement within the bounds of the uncertainty principle. Yeah, it's impossible to know all properties, and this is not something that can be fixed by making better measuring tools. This isn't, hey, right now, based on, whatever instruments we have for measuring things, we can only know down to this precision what something's speed or position is. But, if we get it better, maybe we could figure it out with a little bit more precision. That's not the case. These are fundamental physical quantities. It is not possible to know things like position and speed absolutely. In addition, some processes are random. There's absolutely no means to predict when it happens. Radioactive decay, for example. If you have a radioactive atom, you cannot say, regardless of how long that atom has existed, you cannot say, hey, this is the point at which it's going to decay. It's either, it's at some point in time it will decay, and you have no idea up until then. What you can do is you can know, hey, for this specific isotope, it's more likely to decay in like a shorter period of time versus a long period of time. So you can get like averages basically, but you can never say specifically individual behavior. That's impossible to predict. In addition, particles can be in multiple locations at once. That's called superposition. Because if you think about this probability field of the electron right here, the electron, it isn't that the electron only exists in one location and we're not sure. It's that the electron is simultaneously existing in every single one of these positions at one time. And it is only when we observe it that it chooses a specific location, and where it actually ends up is based on probability. But before that happens, it is in every single one of those locations at the exact same time. So what? Why does this matter? This matters because it means that many things cannot be exactly measured. There are a lot of things, there's uncertainty that is inherent to the universe. And regardless of how advanced our technology or our methods get, there's nothing we can do to get rid of that uncertainty. Also, some things are impossible to predict. It, again, does not matter how good our methods get or how good our technology gets. Some things happen, and we might know the mechanism why it happens, but we can't say when it exactly is going to happen. So some applications of quantum mechanics. Lasers, that is one application. Here we have laser Will Pollock. And if it wasn't for quantum mechanics, he would not be known as Laser Will. Also, semiconductors depend on quantum mechanics with the idea of band gap energy. MRI machines and MRI scans, that depends on quantum mechanics. And just nuclear technologies and energy fundamentally relies on quantum mechanics. Next up, we have chaos theory. Chaos theory was originally, it's something that going back in time, people have understood that things are kind of chaotic. But the recent developments in chaos theory, modern chaos theory, really started in 1961 when MIT professor Edward Norton, Lorenz, pictured right here. I think that the real Edward Norton, the actor, should play him in a movie one day. I think that'd be a fun little thing that could happen. He created a weather simulation program. Basically what he did was he created an idealized, computerized version of the Earth. And then he had, based on just, physical equations, he had weather fronts, temperature, all of these things interacting with each other. And this really was a big thing. This was kind of the beginning of digital computers. It was something that wasn't really possible before the invention of the digital computer, because you get these iterative processes, one step building on top of another, and automate it. One day he decided to run a weather program. He ran it and got one result at the end. And after he got this result, he decided, hey, I want to investigate in a little bit more depth what was going on. So this computer at certain amounts of time, it output logs of, all of the variables in the program. So he took the logs from halfway through the program that had the readout of all of the data. He took all of the data from the log, typed it back into the computer, and ran it again, thinking that he would basically be replicating the second half of the program that he had run earlier in the day. However, while the program matched his data at the beginning, over time it began to diverge, and by the end of the program, it was completely different. There were really no similarities between the original version of the program and the program that he ran using data from the logs of the computer. So this really confused him. So he went back thinking maybe he had input the data incorrectly. And what he discovered was that the computer was calculating everything to 6 decimal places, as we see represented here, whereas his logs were outputting things to 3 decimal places. However, most people at this point, if you would ask them, hey, if you're running you're doing some sort of mathematical problem and you have 3 decimal places versus 6 decimal places, they would tell you you'd probably get, fundamentally you would get the same answer. There might be slight differences, but the general behavior is going to be exactly the same. And what he learned was that was not the case. And upon investigating this more, he started the field of chaos theory, which was based on the idea that complex systems can follow deterministic laws. That is, complex systems follow the rules of physics, yet they are highly sensitive to initial conditions. So what this means is you can have 2 systems that are both run on the laws of physics, and you can just have the slightest difference between the initial starting conditions, and over time, the 2 simulations will get more and more different until they don't have anything in common. And it's kind of reflected in the common, this is attributed to a lot of different people, but the common saying, for the want of a nail, the shoe was lost. For the want of a shoe, the horse was lost. For the want of a horse, the rider was lost. For the want of a rider, the battle was lost. For the want of the battle, the kingdom was lost, all for the want of a horseshoe nail. So this basically shows us that you can have something that's a very, very small, something that is almost trivial at the beginning, but over time it amplifies and it feeds back into itself and makes it so that you have huge drastic changes based on what was initially a very trivial difference. So chaos theory is often brought up with weather, and that's because you think about computers, and the computer that Lorenz was running on was calculating on the order of like a couple of operations per second. It could do like a few calculations per second. And now you have supercomputers that can run quadrillions and quintillions of operations per second. Yet despite that, we can't reliably predict weather more than like 10 days out. And I was reading some academic papers about it in the research for this, and it's thought that even if we had major advancements in both our computing capabilities and our ability to actually like get data for weather, it would be very difficult to extend predictions beyond 14 days. And there's also been hypotheses basically that even if we had some sort of global system that was able to perfectly measure temperature and pressure and wind speed, all of these things, at every cubic foot on the entire Earth, that's going all the way up through the atmosphere on the entire Earth, if we took all of those data points and we fed it into an infinitely powerful computer, we couldn't predict weather more than a month out. And the reason for this is, if you think about it, like let's say we are collecting data for every cubic foot. There's weather that exists in between each of those cubic feet. So you get the data points and then you start running the calculation. However, the second after you take those data points, the weather from between those cubic feet spread out to all of the other cubic feet. And then, a few seconds later, what you have, pretty much matches what you're simulating. But, a day later, there's some pretty fundamental differences. And then eventually those differences get bigger and bigger and bigger until a month out, the weather that you predicted doesn't even come close to what what's actually happening. Another example of chaos theory is, let's say you want to calculate or you want to determine how long the coast of Britain is. How would you do that? If you wanted to determine how long the coast of Britain is, what process would you want to go through?
I'd send a guy jogging along the coast with one of those wheel things that rolls along. Yeah.
That's one way to do it.
Send him to do the loop.
Okay. Are there other ways you could do it?
If you tasked me to do this right now, what I would do is I would boot up my map my run profile and then like make a run that goes around the edge of the thing on Google Earth.
Yeah. Dad, if you wanted to chart out the length of the coast of Britain, how would you do it? You're muted.
Hold the space bar.
I think he's on a tablet.
Oh, okay.
I think, let's see if I can unmute someone.
Oh, I can probably unmute him.
Oh, there he is.
Okay, you can hear me now?
Yeah.
Okay, what's the question again? What would I do if I
If you wanted to measure the length of the coast of Britain?
I would go, I know my foot is about 11.5 inches, so I would go foot by foot.
Okay, so you can get very different measurements based on how you exactly go about measuring it. So if you take, I think this is a 200-kilometer long stick. If you took a 200-kilometer long stick and tried to measure it, you would get one answer. If you refined that down and you got a smaller stick, you would get another answer, an answer that is in fact a little bit longer, because all of a sudden you can see here these bays and inlets and things like that all of a sudden are being measured instead of going straight past. However, if you do what Robert did and you have a guy with a wheel and he's walking around the entire thing, he might walk in every single nook and cranny, right here, right here. And if you're a snail, you would be measuring the nook and cranny between every single individual pebble if you try to go around the coast of Great Britain. So the answer is, it depends. There is no simple way to measure something like this. Really, the only way you can compare the coast of different countries is agree upon some standard measure and then say that the differences in measurement between them wouldn't really matter. If one place has more nooks and crannies, it might be undercounted. Place with less wouldn't be as undercounted as much, but you just need to kind of agree upon a standard method of doing it. Robert, are you going to say something?
Yeah, you could describe, you could describe the coast as a fractal then, right?
Well,
Uh-oh.
here we come to the idea of fractals. So fractals are objects which appear the same regardless of how far in you zoom. So on the left here, we have the formation of a fractal. Basically what you do is, this is an example of one type of fractal. It's called the Koch snowflake. So you can take a triangle, and then on the middle of this edge, or each edge, you put another triangle. And then on the center of each of those edges, you put another triangle. The center of each of those edges, you put another triangle. And if you keep zooming in further and further and further, this shape stays the same. Regardless of how far in you zoom, the shape will never change. And what this also means is that this type of fractal has a limited surface area, because you can draw a circle around this fractal, and you know that the circle around the fractal has a greater surface area than the fractal itself. However, it has an infinite perimeter, because there are infinitely small nooks and crannies, which if you measure each and every one of them, it just causes it to explode. So going back to the coastline problem, if you want to measure it fine enough, you could make the coast of Britain pretty much arbitrarily large. You could keep going to more and more fine measurements, and every time you do that, the length would go up. So what this really points to is that even if you measure something, that measurement might not necessarily reflect the best. Might not. The question is, what does it reflect? Because if someone asks you what's the coastline of Britain, you could get 1,000 kilometers and you could get 1,000,000 kilometers, and it's only whatever people decide is the best way of doing it is the thing that's led us to get the standard agreed upon answer. Pat?
You can also apply the same principle in 3 dimensions, where you can have something with a finite volume but an infinite surface area. Or I might be saying that backwards, but I remember doing it like in high school calculus, where it's the same principle, where but just 3 dimensions.
Yeah. You think about your lungs, and you think about the surface area of your lungs. They don't take up that much space, but they have a huge amount of volume. Or sorry, a huge surface area. And that is because they have just so many nooks and whatnot. So why does this matter? Why does Ks3 matter? What it means is that it may be nearly impossible to measure with enough certainty to make long-term predictions. This does not, however, apply to everything. There are plenty of things that we can predict fine. You think about the motion of the planets, that's something that we can, at least for timescales that we care about. Dad, you have a question?
Yeah, I had a question. One thing to think about too is high tide and low tide.
Yeah, so that's another one right here that we'll be discussing. So yeah, you think about moving the planets, and over the time periods that we're concerned with, we effectively know the motion of the planets. However, I remember in one of my physics class in college, the professor was talking about chaos, and basically the fact that the amount that something deviates goes up by like the square of the error. And basically what he was talking about is that even the motion of the planets, the exact motion of the planets itself in our solar system, we can't really predict beyond, it's like a few 100 million years or something like that. We can't say with like, the planet was exactly here, because there are very slight errors that, they compound. So, you think about tides, and a lot of people might think, and this is actually what they thought back in the 50s and 60s. They thought, we can predict the tides fine. Whether, the tides, a fluid system, it's water. Weather, a fluid system, it's, water vapor and some liquid water. They thought, if we can predict the tides, with a computer, surely we can predict the weather. However, what this is ignoring is that it's the concept of periodicity. So periodicity means that something repeats over some period of time. So, you think about the Earth going around the sun. That's a periodic relationship. It's once per year the Earth goes around the sun. With tides, the things that we care about are the periodic things that come from tides. When high tide is, when low tide is, that's what we care about. There are plenty of things in tides that aren't periodic, but those also just aren't the things that we care about. Likewise, with weather, when it comes to the forecast tomorrow, that's non-periodic. With weather, we care about the non-periodic thing. But there are plenty of things that are periodic with weather. I mean, a prediction with weather is that in the northern hemisphere, December is usually colder than July. That is a periodic prediction. But the thing is, that's just considered like intuitive, and that's not something that we really necessarily care about. Whereas, there are relationships in tides, like Pat and I were talking about rogue waves the other day. And, rogue waves come from these fluid phenomenon. And, you can't really predict when a rogue wave is going to appear, even though it is, again, similar to tides, it is a fluid relationship. And that's because, it's a non-periodic relationship. It's something that doesn't happen at a set specified time. So we can't really predict it. And also weather versus climate. I've seen like memes online where people say like, we can't predict the weather 2 weeks out. How can scientists say that the world is going to heat up by 3 degrees in 50 years? And that's because climate is much more periodic than weather. There's a fundamental difference between weather and climate. And also, if we're like predicting temperature on like a long-term timescale is something that we're pretty good at. That's something that is not nearly as difficult as predicting what the weather a month from now is going to be. What chaos theory also means is that knowing fundamental principles isn't enough. Because, I mean, if you think about it, particle physicists have discovered pretty much almost everything they can discover, and they discovered pretty much everything they can discover like decades ago, but there are so many fields of science we don't know that much about. Like, you can't take the fact that, oh, we know how the electron and the proton and the neutron interact with each other, so, we should be able to know when someone gets cancer, because, a human body is just electrons, protons, and neutrons interacting with each other. So, why can't we just combine, our model for all of those, those three things into one computer program and then simulate a human body based on that. It's because knowing first principles really isn't enough due to the fact that the way that all those things interact with each other is a lot more difficult than the behavior of just individual parts. And just from reading about chaos theory, it seems like that's kind of one thing that a lot of physics education kind of does to disservice people, is that in a lot of physics, we abstract our way or we approximate our way so that all of the things that make systems difficult to understand and chaotic are approximated away. Like, you know, if you think about, if you're told to do, like, let's say you're asked to do a physics problem about, you know, you shoot a cannon, how far will the, you know, artillery round go? But you're told, you know, neglect things like air resistance, neglect all of, you know, things like that, where things that make the actual relationship fundamentally hard is neglected. And that's because it's much more difficult to solve these types of problems when you have, they're called nonlinear terms. When these nonlinear terms are part of your calculation, it's much more difficult. And what it causes is it causes a lot of people who do, you know, college level physics class, introductory physics classes, they think that most problems that can be solved are simple problems that are periodic and don't have nonlinear terms, because all of the problems they've been asked to solve have been in that form, because that's really the only thing we know how to solve. Also, you know, going back to the measurement of the coast of Great Britain, measurements themselves may be ambiguous or poorly defined. Taking a measurement by itself without understanding how that measurement came to be doesn't really mean anything, because different ways that you measure things can cause different results. And that's actually part of quantum theory too. The way that you measure things affects what you get as a result. So applications of chaos theory, really the biggest place where it has applications is influencing decision-making and models, because prediction isn't absolute. Like if you look at this prediction of a hurricane's path to the right, you can see at the top it says, note, the cone contains the probable path of the storm center, but does not show the size of the storm. And that's, you know, taking chaos into account. They're basically saying, we have an idea of the general path of this hurricane, and we're pretty sure it's going to fall within a certain area, but they didn't put a line down. A line would imply this is the path of the hurricane's going to go. Instead, by putting this bubble around, they're saying these are the most likely places that the hurricane could go, but we can't really say where it's going to go exactly. Also, chaos theory means weather modification is possible. The scientist John von Neumann back in the 50s was a big proponent of weather control, and that was before chaos theory was really known. And what he said, it was basically like, if you think about a pencil that you're able to balance on the tip of its lead, it wouldn't take very much of a poke for it to fall any specific way. And John von Neumann's point was that with weather, if we would find these specific locations to insert some sort of relatively small change, that could have effects down the line. It could have multiplicative effects. But he paradoxically didn't take, even though that seems like a very chaotic interpretation to make, he didn't really take chaos into account, because what he neglected to take into account is that, first of all, if we say, hey, we're going to intervene in weather at some point, at that point that we decide to intervene, we would not be able to predict what the weather would be like if we hadn't intervened, and we wouldn't be able to predict what the intervention will do. So, you know, we might say, hey, if we, you know, interact at this one point, we can change the weather, but we have no idea how it's going to change it. And then, you know, 2 weeks down the line, once we have different weather, we can't go back and say, hey, this is what the weather would have been like had we not intervened. So you can intervene in something like weather, but you're doing an intervention where you have no idea what you're doing or what would have happened otherwise. So it's an intervention that, like, you know, the question is, why would you even do it? It seems like you're kind of just, you know, shooting in the dark at that point. So bringing it all together, bringing all three of these concepts together, really the important point to take away is that there are no absolute measurements. Many things happen completely randomly. Well, going back to there are no absolute measurements, that goes back to relativity with time and space contracting and expanding. So that makes it so that you can't even agree upon what measurements are. And then also from quantum mechanics, there's a certain precision to which you cannot get measurements more precise than that. Many things happen completely randomly. That, again, is a quantum mechanical effect. Even small differences in initial conditions can make huge differences down the road. That's chaos theory. And you can only predict the future if you know everything and have a perfect model. You need both of those things in order to predict the future absolutely. This is probably not possible. In order to do this, you would probably need to make a second full copy of reality and have it running in parallel with our reality, in which point, like, what's even the point? So this runs contra.
Nathan, I thought it was definitely not possible.
I would say it's definitely not possible
because of quantum mechanics itself.
So when I say it depends on what you define the future as, partially. If you define the future as 10 seconds from now, you can predict the future with a pretty decent amount of approximation on a large enough scale. Not on like a quantum scale. On a quantum scale, it's not possible. But
so all I mean by that is I thought it was like proven definitively that the universe is non-determinative, to use like the specific lingo.
Yeah, so it's kind of weird. The universe is deterministic in a sense of everything is happening. Well, I would say this: the universe is physical. Let's say that. The universe is physical. Everything that's happening is happening physically somewhere, but it's not deterministic in that if you know the start, you can predict the end, because there are random things happening. And you get a whole bunch of weird stuff from this. Like, have you ever heard of the multiverse or multiple universes? That all comes from some interpretations of quantum mechanics. The thought basically being, what makes one universe where something happens more valid than another. So it's basically, there's something called like particle spin. It's a property of particles. It doesn't matter specifically. But when you measure particle spin, it can either be up or it can be down. But before you measure it, you have no idea if it's going to be up or down. And there is no way of predicting it beforehand. And it's completely random what it's going to be. So the multiverse hypothesis, I'll call it, says that when you interact on a particle and it decides its spin, it can either be up or down. So what the multiverse hypothesis claims is that reality branches and it creates one universe where the particle had like an up spin and a separate universe where the only difference is that it has a down spin. So I think the way that this is thought could be tested is something called quantum immortality, which is that if you could hook yourself up in a machine where when you press a button, it measures the spin of a particle, either up or down. And when it comes up with an up, it kills you instantly. When it comes down with the down, nothing happens. So the thought basically is that you could possibly prove this if you hooked yourself up in such a machine. You can only observe the universe that you are currently living in. If you did this 100,000 times, 100,000 of the times you would die, but there would be, there's a potential for that one time that, 1 out of 2 to the power of 100,000, that percentage of the time you would survive doing it 100,000 times. And you could say with like that level of certainty that the universe did in fact branch. That again is kind of outside the scope of this. And I don't think I don't know fundamentally how it happens, because if you kind of follow that, then immortality itself might be possible. I guess only if your death would have caused by quantum effects. There's not really any evidence to the multiverse, and even if it's real, it doesn't really mean anything. There's not really necessarily anything that we know of that causes it to have any real significance. But yeah, so you can only predict the future if you know everything and have a perfect model. Like Robert said, it's effectively not possible. Probably not possible. Again, depends on what you mean by the future. Depends on whether you're looking at macroscopic effects or microscopic effects. A big question there is, how much does a specific quantum effect have a role on the larger system? Like if you change the spin of that one particle from up to down, how far down the line would you really need to get before you really see a change in the universe as a whole? And again, you might be able to do this, but you probably need a computer that exactly matches reality, in which case reality is that computer itself. So that runs contrary to, if you talked to I think Laplace was one of those guys, and Newton. They would probably tell you, eventually down the line, if you told them about digital computers, they could probably tell you you could, make a universe simulation program where you could, maybe you would take our localized area, make a computer that takes up, you take our 1% of the universe, you want to simulate that, you make a computer the other 99% of the universe, and you just like calculate out, and eventually you'll know everything that happens. But what this is saying is that
use it to work backwards and figure out exactly what happened during the Kennedy assassination.
Yeah, you could maybe do that, but this is basically saying that's not possible. Fundamentally, it is it's not just a matter of we don't have the tools to do it; it's that there are actual physical limitations that make it so we can't do it. And I mean, the thing is, you could use it to predict backwards, but you could also do it to kind of, call into question the entire idea of free will, where you could predict exactly what you're going to do tomorrow. And, if this computer is predicting everything exactly, there's nothing you could do to change that. Pat?
This is the strongest argument I've ever heard that we are actually living in a simulation. I think that this pretty much answers the question. Yes.
Why do you say that?
Just based on everything you've just talked about, someone has created a simulation in order to, do something very mundane, figure out the best way to sell Teslas or something.
So, there is one of the quantum mechanics conspiracy theories is that quantum mechanics' lower limit on the measurability of things is basically whoever made the computer simulation putting the lower bound on measurement. Because it would take, increasing computer power to say exactly where something is. So they basically added a fudge factor to all of the particles to be it's around here. So that is a simulation conspiracy related to quantum mechanics. So fools and charlatans. So my biggest point is really that you look at Palantir, Thiel, financial models, Zuckerberg, all of these guys, they seem like people who think that you can turn people or systems into clockwork, where you can predict things exactly. And one of it's a quote that on the surface doesn't really seem all that harsh, but the more you think about it, it does. It was a physicist who was commenting on financial models. And he said that a lot of economists who make financial models, the reason why they try to turn everything into a periodic behavior is that that's the most complex thing they can imagine. So they don't understand there's a lot of chaos built in. So yeah, basically my point here is that I think that the dudes like this who are trying to basically digitize and datatize everything, they are fighting against the fundamental laws of physics in that, first of all, going back to the data thing, and that was, I think, I remember someone I think was discussing it, or maybe was posting in the group chat, these guys have a problem with data sets. Their data sets are very messy and noisy, and they haven't really found a good way to automate computer analysis of it. But the thing is, data sets are inherently messy and hard to work with unless you're doing data that is so pristine that it doesn't really have any real effect on the world. And then also, even if they're able to get, relationships from these data sets, it doesn't necessarily really mean anything. Because again, if they're off by even a little bit at the start, way down the line, they'll be really far off.
So what you're telling us is we don't really have to fear Palantir. They're not a threat at all, or the NSA.
I wouldn't say they're not really a threat at all. I mean, they still have a lot of data. I mean, if you believe in privacy. What I'm saying is that, the effect to turn people into automatons is a lot more difficult than I think these guys think. And, financial models, I think I've posted some JP Morgan's financial models, and they are complete junk. There are people who have no idea what they're doing, and there are people who have a really good idea of what they're doing that make models that are complete junk. I know that Nate Silver is kind of a meme at this point, but his models I think do a good job. in the sense that he builds models that predict elections. But the thing with his models is that with his models, he feeds in polling data and then uses it to predict an election. However, he doesn't assume the models are correct. He assumes the models are he doesn't assume the polls are correct. He assumes the polls are incorrect, and his model is trying to determine what are the odds that the polls are incorrect. So it is feeding in data, and it's telling the model, hey, treat all this data with skepticism. Use prior analysis in order to, see what it is. And he doesn't claim any level of certainty with his predictions either. I think it's more when you get into a lot of the more like hack model makers, the people who said Hillary Clinton had a 99% chance of winning the election in 2016. And Nate Silver was not one of the people who did that. He was one of the people who said the world is way too chaotic to really say someone has a 99% chance of winning an election with the data that we are seeing.
I thought you were going to say Palantir mapping out pre-crime and stuff like that.
Oh, yeah, like Palantir mapping out pre-crime. I mean, like that type of stuff. Or it was a dude in Tampa who was mapping out pre-crime. I would say even if you had a complete model of an individual's brain, it would probably be difficult to say if that person was going to pre-crime or their pre-crime is going to turn into crime. So to say that like you can take like aggregate socioeconomic data and then get like individual pre-crime out of it is absurd. Any other questions?
What is pre-crime?
So pre-crime is so Palantir is a pretty like evil company that basically what they do is they like analyze everything and they try to make these computer models to analyze things. And one of the things their computer model has been on is basically they feed in information from like a person and then try to predict if that person's going to commit a crime sometime in the future. Mm. Have you ever seen the movie Minority Report with Tom Cruise?
No.
Okay. Well, if you ever do, that would be an example.
It's a concept from that movie, and it's like it's a science fiction movie that is like predicting what the future would be like and like speculating what if there was a future where we could predict crime before it could happen, and what would that mean for the world?
Yeah, so it's basically in this movie, what they do is they arrest somebody and they basically say, hey, our prediction method says that you are going to murder someone tomorrow. So you are under arrest since you were going to murder someone tomorrow. So Palantir...
The difference is that movie has magic and Palantir doesn't.
Yeah, that movie basically has people who can see the future and they're the ones who say it happens. Whereas Palantir is trying to use like computer systems to say... Basically, I think it was in Tampa, there is a sheriff that like preemptively like arrests people and harasses people because he has some computer model that says that they are going to commit crime in the future. And what I'm basically saying is that computer model is bunk and it might get some people right, but it's almost certainly getting some people wrong. So you might be at the same level, maybe slightly better off, maybe slightly worse than just picking names out of a hat and arresting those people for pre-crime.
Thank you.
Yeah. Any other questions? I think too, so one reason why these dudes might not be complete charlatans is that, again, sometimes macroscopic or large scale things are a lot easier to model correctly than small scale things. So like Mark Zuckerberg, for example, he might not be able to say with absolute precision how a change on the Facebook website would affect any individual person, but they often have a pretty good idea predicting how it will affect the site as a whole. Like I think they did some internal study where they changed around the site layout and they predicted how that would change how people interact with the site, and then that's how it changed it. That's still a pretty large step away from completely manipulating human behavior. But the thing is, for Mark Zuckerberg, if it's able to work on 60% of people, that might be good enough for him. He might not care about individual cases.
Yeah, what I was going to say is targeting ads on Facebook. Like you can see what specific targeting groups you're in, and they're not great. Like they are not doing a good job on an individual basis of marking down what you are. But I think in a whole, if you're to use them to target your ads towards a group, it would be like factors like maybe 5, 10 times more efficient than just maybe 50 times more efficient than just sending things out across the internet.
Yeah. And so going back to financial models as well. Guy's name was Mandelbrot. He was the one who invented fractals. He was a mathematician for IBM. And he worked in a lot of fields, but one thing that he discovered is that a lot of economic trends are completely random. Like there was, prior to his analysis, it was thought that, some things, like he analyzed the price of cotton because cotton had records going back a long time. And the common thought back then was that, day to day, the price of cotton might change fairly randomly. If you look at a specific stock, its price kind of going up and down, looks like it's changing randomly. However, his thought was that the overall trend of price changed due to like worldwide events. Things like wars, recessions, that type of thing affected the overall trend. He was the first to do a really in-depth analysis using the theory of chaos, and he found that the price of cotton pretty much increased constantly regardless of what was happening in the world. Like even through the Depression, through world wars, it really didn't change. And he also found that the day-to-day changes were not random. All of that is a completely different lecture, but again, economists trying to make their models fit some reality, a lot of it is just black magic. Not even black magic, it's just bunk. It doesn't work. I think that the consensus...
Marketing.
Well, yeah, it's marketing. It's effectively, I think, marketing. And I mean, the consensus among a lot of modelers back in the early to mid 2000s was that due to our ability to control interest rates, recessions as we knew them were largely over. Because we could predict with such certainty all these things were happening, and then the subprime mortgage crisis happened, and we had the worst recession since in a long time, the worst economic downturn since the Depression. So models don't capture all behavior; they don't accurately really predict behavior. What was his name? Nassan Taleb talks about black sheep events, but I think it goes beyond black sheep event, or say black swan, because black swan events basically say that you can model the day-to-day stuff fine, but you'll have these out of the blue, wild, crazy events that very, very rarely happen. They'll just throw everything into flux. But I think even day-to-day,
Donald Rumsfeld is the one who really pioneered that.
Yeah, old Donnie. With his talk. So his talk of known knowns, known unknowns, unknown knowns, and the even more fun unknown knowns, those are real things. He didn't really do a good job of describing it. But basically, known knowns are things that we know. It is, we know it and we know it. Unknown knowns are things we have yet to discover. Known unknowns are things like this, where we know we don't know a lot about these types of things. Like quantum mechanics, we know we don't know a lot about it, like old Richard Feynman said. And then unknown knowns are probably the most nebulous of them in that they're things that we know, but we don't realize it. So I don't have any examples for those off the top of my head.
It'd be hard to find unknown knowns.
Yeah, because I think by virtue of saying that if you were able to describe it, it wouldn't be unknown anymore.
Yeah.
Does anyone else have any questions? Oh yeah, in case anyone's wondering, Mark Zuckerberg, Palantir, Elon Musk, Peter Thiel, and some book on building financial models.
Can you hear me now?
Yeah.
He's been trying to talk to you for 5 minutes.
This. All right. When did Rumsfeld say that? Or what was the question? What was the question?
I think it was around the time of Iraq. One minute. I'll look it up. I think he was explaining why Iraq was going so poorly, and he used that quote.
What a great answer, though. I mean.
Oh, yeah. Okay. So
coming out of your head.
Oh, here it is. It was in response to a question regarding the lack of evidence linking the government of Iraq with a supply of weapons of mass destruction. So it's basically, he was asked, hey, you say that Iraq is, sending out these weapons of mass destruction to terrorist groups, but there is no evidence that that's occurring. And then he used this as his reply. So I think he was saying that
chaos. There's chaos theory.
Well, I think he was saying that
I think he was saying that we don't want the smoking gun to be a mushroom cloud.
Yeah, and I think he was also saying he was effectively saying we don't have evidence, but everyone knows it's the case. Because, there are known knowns, unknown knowns, known unknowns, unknown unknowns.
So that would be an example of a known unknown.
A known unknown or an unknown known?
We know that they have unknown nuclear weapons.
Yeah.
So that's a known unknown.
Yeah.
Well, he summed it up. The ones we don't know, we don't know.
Yeah.
Great, Dan.
Yeah. Good old Donald Rumsfeld. Does anyone else have any questions? As you can see, the universe is not quite as simple as Sir Isaac Newton thought. But I mean, the thing is, considering his physics do match our day-to-day world pretty well, and he was definitely a step beyond the thinking of the time. Like I said, all this stuff is very unintuitive, counterintuitive even. And if this stuff was obvious, it wouldn't have taken us this long to discover it. Something like chaos theory might not be possible to discover without computers, because unless you have 1,000 people all crunching numbers by hand, and then you plug in data streams from halfway through with slight changes.
Well, I mean, all you need is a pachinko machine. You don't need a computer to look at a pachinko machine.
So that's the thing. There are examples of chaos, like the pachinko machine. Was that from The Price is Right?
I think so. I'm not sure.
If you think about a pachinko machine where you drop a hockey puck or whatever, and it hits. I'll show. I'll show an even better one.
Yeah, where's the pendulum? Where's the double pendulum?
Yeah, I can do that too. The reason I do double pendulum is that this thing only has like 3 frames per second, so it's hard to show.
That's true.
Yeah, any 3-body problem. I was just going to say, while you're getting that pulled up, Nathan, that my education in all of this primarily comes from Bill Bryson's 2004 book, A Short History of Nearly Everything. Not that Bill Bryson.
Our teacher?
Not our teacher. And I got to say, for like a British popular travel author or whatever, Plinko, okay. It was an extremely informative book about all these topics. I have a bone to pick with pop science books in general, but I thought that was an excellent one because it was written by a non-scientist, I think.
Yeah. So what this machine basically does is you drop a hockey puck or whatever, and it drops down. It branches at each spot and goes one way or the other. This is an example of a chaotic system because you can be told where it ends up. Like let's say you're out of the room, it gets dropped, you show up back in the room and it's at the bottom. You really can't predict anything about where it was dropped from where it ended up. It's effectively a black box.
But like the chaos, you can maybe give a probability distribution. But
yeah, you can maybe give a probability distribution.
Of the Plinko machine.
The taller it is, the less you know. And that's like if you see foam at the bottom of a waterfall, you see one clump of foam close to another clump of foam, bottom of a waterfall, you can't really say anything about where that water was above the top of the waterfall. Double pendulum is another very famous one. I found a really good, how well can you guys see this?
We can see it fine.
Yeah.
Okay. Yeah, so all of those started at approximately the same position, and you see they're all already pretty different. And it's a chaotic system. I found there's this really good like program online I found where you could actually set like the angle and the length and everything. And if you changed the angle that it was dropped at by 0.1 degrees and everything else was the same, after 10 seconds, it would have completely different motion. So yeah, if you look at it, just looking at it, it looks like they are starting at the same location. But after 10 seconds, there's not really, looking at any individual one of those, you can say absolutely nothing effectively about where it started, and you wouldn't even predict that all three of those started in the same location. Another fun one is water wheel. Is a Lorenz water wheel named after the, is it Malthus? Yeah, either way. So this is named after the founder of quantum mechanics, the founder of chaos theory. And basically what you have is you have a wheel. You can think of any type of wheel with a spoke in the middle so it can turn, and you have cups lining the perimeter. And each cup has a small hole drilled in the bottom, and then at the top right here, you have water that pours down into whatever the top cup is. And with this, let's see if we can get a good picture of this. With this also exhibits chaotic movement. Because the water is continuing to pour down from the top. Water is continuing to drain out from the bottom of each cup. But as these two started in almost the same location, they're 1 degree different. Over time, their movement will get very different. And you can see, at first, they seem like they're about the same. And that's another thing with chaos theory is as, your computers get more advanced and your measurements get more advanced, you have better and better approximations of the real behavior, and you can stretch it out further. But ultimately, you'll be met with chaos. See, at this point, they are completely different. And you can see also, so something with the water wheel is a lot of things in physics, people like to say it like oscillates or has periodic motion. With this water wheel, it is pretty much randomly reversing direction, changing speed. There's not an easy way to model this behavior.
There's a similar kind of example in computing where if you give two identical processors the exact same pieces of code, they will execute the instructions that it transfers down into at like the machine code level in a different order. Just because the differences in heat between one processor and the other will decide that it's more efficient to put this instruction above this instruction. So it'll give you the same result because it'll execute, but it'll do it differently.
And you think about this water wheel, you would, just look at this water wheel, you would think this is something that's easy to simulate. There are a couple dozen wheels of water, it's spinning, surely that's something that you could, a lot of people think they could just intuitively know what's going to happen. But really that's not the case. And then you think about, think how much more advanced or how much more complex the human body is, or society and civilization is compared to this water wheel. And then you get people who claim that they have intuitive understanding of how the economy works or something like that. And it's kind of absurd. You get the old, I think it was Chile, where they had a command center for running their economy. Well, I'll see if.
I think there are other things to be said about Chile's economy too than just that.
Yeah.
I'm gonna stop recording.